administrative things. So one, for those who didn't pick it up last time, the midterm is up here in the front, so please come grab it. If you're watching this on the web and you still haven't gotten it, it'll be available in my office. The only other sort of logistical related note is I will actually be out of town starting later this evening. So Pierluigi will be doing our lecture on Thursday. I'm sure he'll do a great job. I'm working with him to make sure that's all prepared and everything like that. So that just only means that I will not have my own office hours on Thursday, but Pierluigi will still have his office hours on Friday, and we'll both obviously be available over email in case people have any questions. So other than that, how many of you guys have actually started homework number 4? I see. So everyone's going to have an enjoyable spring break working on that. So just another reminder, do get going on that. It is a bit of a design project. So you should expect to be spending a reasonable number of hours sort of tinkering on it. We've obviously gone through some example design procedures here, but I've somewhat intentionally left these design procedures not fully ideal because, again, the entire point is for you guys to go through and try and synthesize that for yourselves on a more quote-unquote complete or realistic design. So again, that's most of what homework number 4 is all about. Make sure you leave yourself enough time to do it. Don't just sort of party all spring break and then try and do it the night before. Trust me, it won't work very well. So, any questions on either class material or anything like that before we dive back in? Or I did forget to mention one other thing. In terms of the midterm, we always put together a sort of grading criteria and try and make sure that we followed that criteria. If you look through your exam and you think something doesn't make sense or anything like that, which basically do is write up sort of what you think didn't quite, that you may not have gotten enough points for or something like that, I'll then take that exam and look at it versus the criteria. The only caveat is that, once you sort of submit it, I will look at the whole exam, not just whatever you sort of pointed me to. So that may work either in your favor or against you because I may find other places where we were either too generous or not generous enough. So that's the only sort of caveat there. But again, we do indeed try our best to make sure that everything is graded on a very uniform scale. But if you have any issues, just please do feel free to come and bug us. All right. So unless there's any other sort of questions or anything like that, let's go ahead and get going again, which is basically wrapping up this sort of example design procedure that we had been talking about. So I believe where we ended last time was sort of on our quote-unquote step number 7, where we had basically said that we'd already calculated all the sizes of the capacitors based on essentially the dynamic range constraint. And now what it was really coming down to is we basically just had to figure out essentially how much GM we needed based upon the dynamic settling constraints, meaning the operating speed of the amplifier and how much we had budgeted to the dynamic portion of the error. And essentially how much loop gain or how much open loop gain we needed from that, our amplifier design, to satisfy the static settling constraint. And we had basically ended on saying that there's always this trade-off here in that, in principle, you'd like to really sort of put as much of the error budget on the dynamic side as you can, because dynamic is really what costs you power. It's just that in practice, that would tend to push up the static gain requirement. And at some point, you may simply not be able to meet that gain with the sort of simple type of topology that you had been working with. So this is where you have to go to sort of cascoding or gain boosting or something like that, which indeed has its own power penalties, but typically is a little bit less than sort of the power penalty of just directly requiring more GM to drive the output capacitance faster. So this is, again, a sort of somewhat iterative process in that once you sort of know reasonably what kind of gains you can target, that would allow you to set the static settling error and therefore would also sort of constrain the dynamic settling error. So hopefully that makes sense to everybody. So the next step that we're actually going to take is now that we've got the capacitors, we've got the required GM, we've actually got the sort of required open loop gain. The next step is actually fairly straightforward, which is essentially just to basically pick the channel length of the transistors. And by the way, of course, the trade-off we'll be making there, or the specs that sort of are being traded off there, are the gain, or the open loop gain rather, versus the FT of the devices. And basically, we can now do this fairly sort of, let's say, rationally now, because again, we already know what the open loop gain we need from our structure is. So as we'd said before, we can always then go and basically look at some plots of our transistors, say, okay, well, with this given amount of swing or VDS across them, how long of a channel length do I need to actually guarantee the gain spec that I'd been targeting in the first place? Okay? So just as an example in this particular design, let's say that I choose my channel length at the input to be something like 1/4 micron. And just as a reminder, I was working in a 0.18 micron process here. So this is a relatively short channel length. And by the way, you do indeed typically want a relatively short channel because remember the input capacitance does actually matter, right? In other words, if you use too long of a channel length, then the FT will suffer, and then that input cap will be large. You'll be paying a large sort of feedback factor penalty. Okay? So again, sort of typical choice here is, this is close to minimum, although not quite at the minimum, so quarter micron. And then the next thing I do is I basically just take my sort of device lookup table, which, again, was much like what you did in homework number 1. Say, okay, well, for this channel length of the transistor, for the V star that I chose, basically, what is the bias current density that I have? And then I can use that to actually calculate how wide the device itself should be. So in other words, what I'm basically going to say is the width I'm going to end up needing is the actual bias current I know I need to be flowing, essentially times the current density. Okay? So what I mean by the current density is, as an example, let's say for this particular technology, I know that I get 8 microamps for every 1 micron of transistor width at the particular V star that I chose, which remember in this case was about 120 millivolts, which is relatively low, which is why this bias current density is also relatively low. Okay? So if I do that and you work out the numbers that I'd written a second ago, which was, again, that bias current was, a few milliamps, then basically you end up with a device width of 587.5 microns. Okay? And by the way, there's an ID number that I plugged in there. ID is like 4.79 milliamps, I believe, or something like that. That's how I ended up with this 500-something microns. By the way, the actual numbers there are not super critical, other than just to give you an example you can double-check down the road at home. Okay, so once I've got this, actually, in many ways, my design is kind of done. Okay? The only thing that I do have to do, though, is kind of maybe go back and check a few of the things that either we'd made approximations about, or even in the first place just made guesses about. So if you guys recall, when we had first done this design, we basically had guessed what the input cap actually was for our OTA, right? And I just kind of came up with some pseudo-random number and argued why it was reasonable. Okay, well, now we actually have a real number, right? I've sized the device, so I should know exactly how big that input capacitance actually is. Okay? So this next step is to actually check what my input capacitance really is. All right? So it's going to turn out that in this particular technology, with the particular width that I chose, you're going to get something where the input cap is roughly 1 picofarad. Okay? We can do a more detailed calculation. It's actually not too critical. It's just going to turn out to be roughly 1 picofarad. Now, just as a reminder, our original guess had been that the input cap was going to be 3 picofarads. Okay? So in other words, our actual input cap is lower than what we had guessed in the first place. So now, here's the question for you guys. Is the fact that our actual input cap is lower good news or bad news? Somebody says it seems like a trick. So why did you say it seems like a trick? Okay, so it would seem like it's good news, but it is indeed both. Okay, so now we have to figure out why it's both. So what's good about this? Why is it good news that the input cap is actually smaller? Say that again? So you said your bandwidth can be higher. That's true, but let's actually, and unfortunately I don't have all of the previous stuff that we wrote, but remember when we were doing the whole design procedure, at what step was it that we had to guess the input cap? What was it that it was most affecting in our procedure? The static error. Okay, it does actually have an impact on that, but indirectly. So why does it have an impact on that? For the input cap? Remember, where was it we had to guess the input cap? Feedback, yeah, right? It was the feedback factor that was changing based on the input cap, right? Because the bigger that input cap, and okay, maybe I'll just draw it here since I don't have it elsewhere. Right, if we draw sort of our OTA and the capacitive feedback configuration, right, we had something that basically looked like this, with all of these actually connected, of course. Right, so this was our CS, this was our CF, and this was our CN, right? And so in order to actually know what that feedback factor was, right, from the output back to the real input of the OTA, which just as a reminder, we always called that capital F, it depended heavily on that CN, right? And we needed to know that feedback factor for all kinds of things, right? We needed to know what it did in order to figure out the loop gain we needed. We needed to know what it did from a noise standpoint. We needed to know what it did from a settling standpoint, right? It basically affected everything that we did, okay? So now I'll ask you guys again. Why is it good then that our input cap came out to be lower? Okay, so you said you can redesign it to use less power. So that is true in the following sense that because my input cap is lower, my feedback factor is actually going to be better, right? So if you guys recall, I believe our feedback factor had turned out to be something like a 1/10. Now it's actually going to be something more like closer to maybe a 1/9 or so, right? So I could basically just take that improvement of 10% or so and just kind of apply it uniformly to basically all of my calculations. Roughly speaking, it would save me about a 10% in power consumption. Okay, that's certainly good. There's actually another sort of way of looking at this which would argue that your Cin being a little bit too low might actually be sort of bad news. But bad news only in the sense of that you could have actually gotten even lower power consumption by doing something else. So, what is the something else you can do from an amplifier or even transistor design standpoint that would exploit the fact that the Cin is lower than you expected it to be to lower power, other than just, as you said, the feedback factor was actually better, so there was sort of a 10% effect there. What else could you? There we go. You could lower the V star, right? Because what this is basically saying is that, well, we did our whole design assuming that essentially the input cap was larger, which means that essentially we could have made the transistor bigger for the same sort of GM characteristics, right? If you make the transistor bigger for the same GM, that means effectively you're decreasing the V star, which would decrease the bias current, right? So indeed, the other sort of way you could play this game is you could say, well, okay, since I got lower input cap than I expected, then maybe instead of using 120 millivolts V star, I can drop that V star to something lower. So by the way, what do you guys, what do you think would be a reasonable choice to try and reduce this to? Just throw out a number and we'll see if it makes sense or not.
40 millivolts.
Oh, okay. So you said 40 millivolts. Okay. So now, is that actually possible? Okay, yeah, you said you want to, you could push it all the way to the flat region of basically where the GM over ID versus VGS is sitting, right? Meaning the best possible current efficiency you can get, or transconductance efficiency you can get. Now again, just as a reminder, what is that limited by? In the flat region, what does the device look like? Yeah, it looks like it's in subthreshold, it looks like a BJT, right? Okay, so in a BJT, the relationship between, let's say, GM and ID is always set by essentially KT over Q. There's another sort of factor of 2 you have to be careful of just because of the way we define V star. So the sort of absolute best you could do is typically something like 50 or 60 millivolts of V star, so to speak. But you have to remember it's a FET and not a BJT. So there's always that N factor of the capacitive divide between the oxide and the depletion region underneath. So typically the best you can really get is something on the order of about 80-ish millivolts or so. All right? So indeed you could push all the way down into that regime. But then of course the question would be, does that mean that your input cap really just goes back up to 3 picofarads, or does it actually go way, way larger than that? And for that you have to look at your device sort of lookup table, obviously, to know. But indeed this is basically saying that you could potentially drop that V star maybe from 120 millivolts, maybe to 100, 90, something like that. And indeed buy back some power consumption that way. Okay? Does this make sense to everybody? Or? Okay, great. So there's just a few more, let's call them housekeeping or checks that we have to do given the design procedure that we just followed. Okay? So the first is that in everything we had done so far, largely for simplicity, we had assumed pure single pole settling. Right? And as we'd spent a lot of time talking about last time, or actually maybe even 2 times before that may not even really be correct. Right? We basically said, just as an example, we're always going to have some feed forward 0 in the system. Right? And again, really just as a reminder as to where that was coming from, if we again draw our sort of capacitive feedback amplifier, we had a CS of 24 picofarads. We had a CI. Let's just assume I didn't go back and redesign it. I'm just going to leave it as a picofarad this time. Okay, we've got our OTA. We've got a CF of 3 picofarads. And we had a CL of, I believe, 5.2 picofarads. Okay? So again, just as a reminder, in this configuration, if you put a step in at the input, then at the output, you'll, of course, initially get a step. And then it'll start settling back down to where it was really actually supposed to go based upon the feedback. Where that initial step was really just caused by the capacitive divider coming all the way from the input through here to the output. Okay? So now, let me ask you guys, roughly speaking in this particular context, do you think that this feed-forward 0 is going to cause a big effect, or it's not too big of a deal? So I'm not even worried about slew rate yet. We'll come back to that in one second. Let's assume the amplifier is perfectly linear. I'm really more just interested in how big of a sort of extra swing are you going to have to do due to that feed-forward 0. Okay? Or rather, relatively speaking, how much extra swing are you going to have to do compared to what you would have had to do no matter what? And I don't need any numbers here, by the way. Just, back of the envelope. Okay, so I think you said all the right pieces, but let me just try and tease that out a little bit more precisely. So let's maybe just take a vote, and then we'll see sort of what people think. So who thinks the feed-forward 0 is going to be a really big deal in this context? Who thinks it basically doesn't matter? Wow, there's like only half of a brave soul. Okay, so how would you calculate this? What is it you have to know to be able to say if the feed-forward 0 really causes a big change in the swing at the output or not? What do you have to compare against what?
Well, the effect it has with respect to the dynamic error.
Yeah, okay, exactly. So you have to figure out what is the effect of that feed-forward 0 on the dynamic error. So if we did pure single pole settling, right, then our output waveform would just look something like this, right? It would just start from 0 and then go down to whatever the final value is supposed to be with some time constant, right? So what did we say was the dominant effect of that feed-forward 0? How would that sort of change this waveform? Yeah, I see a few hand motions. Just, say it out loud. Yeah, it would go up first, right? So if I had that feed-forward 0, what would basically happen is, oh, come on, there we go. It would jump up first, and then it would start settling down, right? What did we say was the way we would basically handle that from a sort of settling time calculation? What's the only sort of modification we had to make?
Initial step.
Yeah, we just basically said that, look, instead of having, as an example, this much swing to do, right? Now we just have this much swing to do, where the sort of increased swing is just set by the size of that initial jump relative to the final value we need to have. Okay? All right, so now let me repeat the question. Again, in this particular context, with the capacitor values that I've given you here, who thinks that this feed-forward 0 is going to be a big deal, meaning it's going to drastically modify your settling requirements? Okay, who thinks it's not? All right, good. A few more brave souls. So, turns out indeed, in this particular case, it's probably not going to be a big deal. So now, why not? Other than just my tone indicated that was the right answer. Yeah, exactly. So there's really just two key things to keep in mind here. Okay? So the first is that notice this CF is kind of a little bit smaller than CL, right? And so the CS indeed is quite big, but remember, to get all the way from the input to the output, I have to go between both. I have to basically go through CS in series with CF to finally get to CL, right? So notice that even though this is quite big, CF relative to CL is, something like 60%-ish or so, right? So right from the get-go, I'm going to get something like a, maybe 60% attenuation between the input step and the output step. Okay, so that's true, but there's actually even one more thing which is very important in this particular context, which is, what's the closed loop gain of this structure? In other words, what's the gain from V in to V out? Ignoring that feed-forward step for now. Meaning, I waited forever, and I just want to know, what's the sort of ideal thing going to do? In general, for these capacitive feedback OTAs, what's the closed loop gain? Is it actually 1 over F, or is it something else? Because remember, this is the funky feedback topology where the closed loop gain is not actually the feedback factor. By the way, what did we say was our target closed loop gain in the first place? Back on slide number 1 of this lecture. Yeah, it's 8, right? Which, notice, by the way, is exactly the ratio of CS to CF, right? Just like your normal resistive feedback OTA. Same thing, just with the numerator and denominator flipped, right? So our closed loop gain here is 8. So if our closed loop gain is 8, we just said a second ago that this direct feed forward thing would be something like 60% of the input, right? But we've now also said that this step down should be 8 times larger than the input, right? So relatively speaking, how much larger of a swing do you have to do with that feed forward 0 versus without? Ballpark. Yeah, well, okay, I would have said it's about 10% or so, right? Because in this case, I have to sort of do an 8x relative swing. In this case, I have to do like 8.6 or something like that, right? So yeah, it has an effect. It'll maybe cost you, another 0.2, 0.3 tau or something like that. But it's not going to be a very big effect, at least in this particular scenario that we're talking about here. Does this make sense to everybody, or? Yeah. Yes, it is. Yeah, okay, so when I say it's 8 to within whatever that static error is, right? But remember, we targeted that static error to be extremely small, right? So it's 8 to within, let's say, 4 orders of magnitude or something like that. Okay, so again, key point here only being that user beware, and the design methodology we used, it was all assuming simple single pole settling. If in reality you have the feed forward, you in general would have to include that, but typically speaking, it's not too large of an effect. It just causes you to tweak that tau by, an extra 0.2, 0.3, something like that. Okay? All right, so the other thing that we have to be careful about, oh, yes, question?
Sorry, just to make sure, the ratio becomes like the divided ratio of the initial swing. Is it just the CL over CL plus CF CS?
Okay, so the question was, how exactly did I calculate this feed forward factor here? To be totally accurate, the exact calculation I did ignored the CI, and indeed I just did essentially CF in series with CS divided by that same thing plus CL, right? In reality, you should include this as well. That'll just decrease it ever so slightly. In this particular example, though, it doesn't have a big effect just because CS is so large in comparison to CF anyways. Does that make sense? Or? Okay, great. All right, so the other thing we do have to be a little bit careful about is that we also completely ignored slewing, okay? And so, again, the way we're going to sort of have to double check that is, and let me just again, one more time, draw our capacitive feedback amplifier. So again, let's just say, size the same way that we had done before. Okay, so that's, let's say, CF of 3 picofarads. Then we have some CL out over here, which is going to turn out to not matter too much, right? So just like before, what we have to do is basically check how bad was our assumption, right? In other words, is it really going to be the case that the thing does not slew, so that we can just assume it's all simple single pole settling? Or will we really actually hit that slewing condition? So again, the way we're going to check that is we're going to say, well, okay, We're going to apply a step right here. And then what we're interested in is how big of a step are we going to get at that Vx node right there. Okay? So again, just as a reminder, we know that the maximum step we can get at the input. Oh, hello, there we go. We know that the maximum step we can get at the input is just going to be equal to our output swing divided by that closed loop gain. Okay? And just to sort of take the numbers we had before, I believe that translated into approximately something like, oh, no, I can't read my own handwriting. Yeah, it was about 120-ish millivolts. Okay, roughly speaking. Okay, so if we know how big that input step is, we can then also calculate how big the Vx step is. Again, just based purely on the capacitive divider from here to this node right here. Yes?
Well, so I mean, that's sort of the largest step that you could reasonably expect to see kind of different here. You could apply a large step, though, right?
Okay. So the question was, this is sort of the largest step that we're in some senses designing to be able to tolerate. You're saying in principle, somebody could just go and apply a larger step into your amplifier, and then indeed it would be larger than this, and the output just wouldn't behave the way we expected it to. That's absolutely correct. Although oftentimes in let's say the context that we're thinking of, we're going to be able to control how big of an input we're applying into it in the first place. But you're absolutely correct. If I just have some general purpose thing, and I say, okay, well, it's built this particular way, somebody could indeed go and apply something nasty into the input, but usually you just say, well, okay, if you do that, I don't guarantee any of the other sort of specs. Right? It's a very good question. Okay, so if I know that this is the sort of largest input step that I'm reasonably expecting to be able to tolerate, I can then check how big the step at Vx would actually be. And again, that's just purely based on the capacitive divider. Okay? So it turns out in this particular case, that's going to be a pretty large fraction. Again, simply because CS is so large. Okay? That's going to turn out to be something about 100-ish millivolts or so. All right? So now, here's the question for you guys. What do I have to sort of take that 100 millivolts and compare it against to be able to decide if slewing really is an issue or not? Yeah. Yeah, exactly. We have to compare this against V star, right? So as a reminder, we said that the V star of our input devices, we had chosen to be 100 millivolts. All right? So in this particular case, I could kind of roughly argue that perhaps the slewing is not a problem, right? Because my input V star is large enough compared to that step that I maybe didn't quite hit a very bad slewing condition. Now, to be totally accurate, by the way, these two numbers obviously are pretty close to each other, so you may start hitting some of the nonlinear effects. But to zero order, at least it looks like we're okay in this particular example. Now, having said that, if we start actually changing or redesigning this amplifier to actually exploit the fact that we said that our input cap was lower than we expected it to be. What did we say a second ago that we wanted to do to actually exploit that? How did we want to change the OTA? Yeah, we wanted to lower the V star, right? So if we lower the V star, we sort of have to be a little bit careful that in the process of lowering it, we don't end up making it so low compared to the input step that we actually have a problem. Now, the thing that may actually save you in that particular context is if we lower the V star, that will increase the input cap, which will tend to decrease the input step as well, right? So you may sort of be just naturally okay, but again, user beware, because indeed there's the possibility that as you try and lower that V star to get a better current efficiency, you'll actually enter the slewing regime, and again, won't quite get the sort of dynamic performance you were expecting. Does this make sense to everybody, or? Okay, so this is actually kind of it in terms of this, let's say, example design procedure. As I had said before, the whole purpose of this is not for you to just take this and repeat it exactly in your homework, but actually to think about what are sort of, how can you actually improve this? How can you do this in a more, let's say, direct way? Or if nothing else, in many of the sort of guesses and feedback loops that I had mentioned, I gave you some examples as to what you might be able to do, but I strongly encourage you to think about it, let's say, from a more formal, more procedural standpoint as to not just maybe be placing guesses into there. Think about how you could actually do this all in a sort of direct manner. Okay? The only last thing that I do want to spend a little bit of time on is just to sort of discuss a little bit as to what's going to happen when you really do this with a differential design rather than with a single-ended design, right? Because everything we talked about was single-ended, but in practice, you're mostly going to be dealing with differential or fully differential OTAs, okay? So in order to do that, I just want to sort of draw both the differential and the single-ended design and make some comparisons about some of the simple zero-order characteristics of those two things, okay? So let's first just sort of draw our simple single-ended design. So as an example, we have a V in there, we have some bias current here, and we have some load cap over here, all right? And again, I want to compare this against the fully differential design, which in some senses is just going to be me taking almost 2 copies of the original structure, just that I am indeed going to use a tail current source to sort of really make it truly differential, okay? So I, for example, have a Vin plus there, a Vin minus there. I'm going to place a load cap on each of those independent outputs, and this would be a Vout minus and a Vout plus. This will again be I bias, and I tail. Okay? All right, so, oh, yes?
We're just going to ignore that it's kind of floating there,
Floating. What do you think is floating?
the transistors.
Oh, maybe my drawing is not perfect, but everything is actually indeed connected.
I mean, like with respect to ground.
With respect to ground. Oh, there's a ground down here, right?
Yeah, but it's all current sources.
Oh, yeah, well, okay. So, yes, all of these are drawn as ideal current sources, but actually, even if I did use ideal current sources, this would bias up perfectly fine in principle. We'll talk some more about the particular issue you might be worried about in a second, but let's pretend I made this I bias exactly half of I tail. Okay? In principle, everything should be fine, other than what you might be worried about is the common mode here. Again, let's pretend that I've done that so that it's all okay. All right? So in other words, what I'm really trying to compare here is essentially this thing as a single-ended amplifier versus let's just pretend there was a virtual ground really at this node and compare it against using 2 of them in a differential configuration. Okay? Again, we're going to have to actually talk, in 1 second about all of the stuff that happens with the common mode. Okay? All right. So let's first just assume that you went and you did the calculation as to, what the V stars in these transistors were, and you knew what the total sort of peak-to-peak swing at this output could actually be. Okay? So just to sort of start things out, if you know what that peak-to-peak swing is, what's the sort of maximum RMS signal voltage you can get? Basically RMS signal voltage that you can get at the output of that amplifier, assuming, again, it's a sort of sinusoidal signal. And just assume that I've told you that the peak-to-peak swing is V swing. What's the sort of, mean squared voltage you get at the output due to the signal, of course? Oh, okay. So you actually gave the final result. I just want to piece it out into a couple pieces before we go to the final one. It's basically 1/2 times V swing over 2 squared. Okay. So why is it V swing over 2 squared? The reason is just remember we said the peak to peak is V swing. If I want to fit a whole sinusoid into there, then the amplitude obviously has to be half of that peak to peak swing. And then the RMS is just 1/2 times the amplitude squared. Okay? Yes?
Sorry, I just can't read what that says in the button.
Oh, it just says V swing over 2 squared.
Sorry, I'm on the left of this.
Oh, that's just V sig squared. That's just like the mean squared signal voltage. Okay? All right, now let's ask ourselves the exact same question for the differential amplifier. So, what is the mean squared signal voltage for the differential amplifier? What's that?
4 times that.
Oh, okay, you said 4 times that. Again, you gave me the final answer, but I'm going to just write it out a little bit more pedantically. So it's still going to be 1/2 times the amplitude. But now, because it's a differential amplifier, I can get double the peak-to-peak swing, right? So as you just pointed out, that means there's going to be a factor of 4 extra signal swing, or signal, I should say, power or energy, in the differential case versus the single-ended case. So that already sounds pretty good, but let's actually do one more comparison. So if I told you there was some gain, known gain from this structure, what would be the output noise of this single-ended amplifier? And the output noise, obviously, RMS. And by the way, if there's some scale factors in front you're not sure about, that's fine. Just give me the most basic thing it's set by. There we go. There's a KT over CL. Okay, and it's going to turn out that if you assume the current source was ideal and it was noiseless and etc., but I told you what the voltage gain was, there would just be some gamma AV times that. Okay? And if you don't like gamma AV, just pretend that that's some scale factor, because it's going to turn out it's not going to matter in the particular context that I'm interested in here. Okay? All right, so now let's ask the same question of the differential amplifier. What's going to be the differential thermal noise RMS? Or variance, I should say. There we go. It's double, right? It's actually going to be 2 times KT over CL times gamma AV. Now, why is it doubled, by the way? What happened there that makes it double? Yeah, there's 2 independent noise sources, right? Each of them would independently create essentially that KT over C on each of their own capacitors. And then when you take the differential output, remember when you're talking about random things, the sign doesn't really matter. Because if they're uncorrelated, then subtracting is exactly the same as adding, right? So in other words, I have double the noise power because I have these 2 independent noise sources that I'm essentially, quote unquote, adding together. Okay? Does this make sense to everybody? Or? Okay, so now, of course, the net point of all this is that if we look at the SNR, right, that's going to end up being something like V swing squared over 8 divided by KT times that gamma AV times the load cap, right? Whereas in the differential case, it's actually going to end up being 2 times V swing squared over 8 divided by KT times gamma AV times the load cap, okay? Where that factor of 2 is just coming from the fact that we have 4x of the signal swing, but double the noise, right? So in other words, SNR-wise, we've improved by a factor of 2. Okay? So now, here's the question for you guys. Did I break any sort of, physics here or anything like that? Or does it actually kind of make sense that your SNR is twice as good in the differential case as it is in the single-ended case? Yeah, exactly. I'm burning twice the power in the differential case, right? I now have 2 I bias as opposed to I bias. So indeed, if I spent exactly double of the I bias in the single-ended case, I could have also actually gotten the same improvement in the SNR. Okay? It's just that I chose to do it typically in this differential configuration, simply because by doing it differentially, I get to reject common mode, I get to not worry about power supply variations, or really just, that's another way of saying, by the way, common mode variations. Basically, I can just build a more robust system out of the differential design as I can out of the single-ended design. Okay? At the end of the day, the sort of fundamental trade-off between power and noise really is the same. Okay? Does this make sense to everybody, or? Okay, great. I was hoping somebody would ask this. So, if I really was to use this topology versus this topology, then indeed, probably actually it'll be a little bit worse in the sense of I've taken away some headroom for that biased tail current source, right? Now, in practice, even when I did this, I would have to sort of bias that transistor in some way, and so that common mode, I may not be able to really bias it exactly in a way that would allow me to really get that extra swing. But having said that, yes, in principle, or rather, if you really sort of paid very close attention to this, then indeed I would be losing some swing to that tail current source, and that would then actually cause an SNR penalty. Okay, so that is actually true. I guess if you wanted to, you could, of course, also always really do it exactly the way I sort of indicated with these dotted virtual grounds. Right? If you really tied that to ground, you built a so-called pseudo-differential amplifier, then the argument I made would be exactly correct. The only penalty, of course, would be that you wouldn't really get as much of the common mode rejection and other benefits that you get from differential that is really, I think, the focus I was trying to point out here. Does this make sense to everybody, or? Yes?
You actually just doubled the bias current in the simulated do. It seems like there may be some other, like it seems like you're not just going to increase your SNR. It seems like there might be other effects, and say like how you emphasize the device and your capacity.
Okay, so that's right. So you said you couldn't really just double the bias current. You'd have to actually do some other stuff to really get the SNR to improve by a factor of 2, and that's absolutely correct. So in this particular case, if you wanted to increase the SNR by a factor of 2, exactly what would you really do? Besides just doubling the bias current. What's really the most critical thing? And I'll give you a hint. Take a look at, the term that I pulled out on the side of the SNR always. Yeah, the capacitor, right? Because at the end of the day, my noise was KT over CL, right? So if I double the cap, I will reduce the noise by a factor of 2 in variance, right? And that's exactly how I would get an improved SNR. Now the point is I've doubled the bias current because if I want the same settling, gain bandwidth, and etc., I double the bias current in order to exactly get GM over CL to be constant, right? So in other words, if I want to keep all else the same, doubling the cap requires you to double essentially the GM and the device size and etc., and therefore the bias current. Does that make sense? Or? Okay, great. Any other questions on this before we move on? Or? All right, so let's go ahead and actually move to the next set of lecture notes, which is now actually going to be discussing a topic which we touched a little bit on before, which is to say that at the end of the day, the whole reason we wanted to do these differential amplifiers was really to gain that immunity or that robustness to the common mode. However, having said that, as soon as you try and sort of gain that immunity, you also then therefore have to worry about whether or not you're really controlling the common mode the way you were supposed to be, or the way it needs to be to actually make the amplifier work in the first place. Okay? So again, just to make sure that that's absolutely clear, let's look at this very, very simple example here. Okay? So here I'm actually drawing exactly the situation that you guys were asking about before, where I'm really going to do everything with ideal perfect current sources now. All right? So I have an IL here, an IL there, and an I-tail down over here. All right? And now let's say that indeed I'm in the quote-unquote real world, only in the sense of I'm still going to have ideal current sources, but they're not quite exactly the value we wanted them to be. Okay? And in particular, let me ask you guys the question of what would happen if IL is actually less than half of the tail current? Okay, so I can even give you some numbers. Let's say I-tail was a milliamp, and IL was only, 490 microamps. So what would happen in that particular scenario to this amplifier? In particular, what would happen to the outputs of that amplifier? Where would they go to? And again, everything is at a perfect ideal current source. Oh, almost. Ground, there we go. Okay, they go to ground because, and again, I'll just write the numbers here to be sure everyone is clear. If I said that I-tail was, let's say, a milliamp, and that each of these was, let's say, 490 microamps, right? Then now, when the tail splits between the two sides, that would be 500 microamps. But I only have 490 microamps to fight against it in the upwards direction. And if I really have ideal current sources, then for all intents and purposes, both of these are just going to get railed out at ground, right? Yes?
My reasoning was, the current is going to have to go somewhere, so it's going to have to flow out of the gate so that the pool doesn't.
Oh, well, so I guess the problem is that there's no, I understand the rationale, although in this particular case, because there's no other sort of impedances anywhere, right? Basically, if I have more current flowing down than I have flowing up, I'm pulling that node down closer to ground. Right, so now, to be totally fair, I am doing a situation that's a little bit weird in that I'm using ideal current sources everywhere, right, which is not exactly fair. But really, it's just saying if you've got more current flowing one direction versus the other, it's going to yank that node in that direction. That's really all I'm saying. Okay? All right, so indeed, this would be bad, right? Because clearly, if your output is really grounded, then nothing's working, right? The transistors won't actually operate the way you wanted them to. Even though in principle, hey, that's just the common mode, but clearly if the common mode bias point is busted, the whole amplifier is busted, right? All right, so let's just see if there's anything that would sort of save us indirectly. And in particular, we said that usually we use these amplifiers not open loop, but in the capacitive feedback topology that we've been looking at for several weeks now, right? So let's see what would happen if indeed we added that capacitive feedback, okay? Which would typically look something like what I've drawn there, all right? So I'm still going to have this sort of mismatch in the current sources, but I'm now adding this capacitive feedback in. So the question I want to ask you guys is, will that capacitive feedback help solve this problem or not? By the way, why is there some hope that it might help? So let me ask another question. If I have a common mode movement on that output voltage there, let's say both sides move up, okay? What's going to happen at the two inputs of this amplifier? Meaning, what's going to happen to the common mode at the inputs of the amplifier? Which way is it going to move? Yeah, it's also going to move up, right? Okay. What would that do to this tail node? Which way would it sort of pull it? Yeah, it would also pull it up, right? Okay, we just said our problem was that we had this guy down over here getting sort of yanked to ground, right? So indeed, if I sort of did a feedback like that, then that would tend to sort of try and pull you the other way, right? Now, here's the question. Why does that not end up working out so well? Yeah?
Sorry, we started with the assumption that we were pulling those top nodes up.
Uh-huh.
But we're saying that those are being pulled down. So I guess I'm not seeing. I see where the feedback is happening if you pull those top nodes up, but it seems like you're starting by pulling them down. How does it?
Oh, so, well, let me maybe take a step back and then I'll sort of point out. All I was trying to say was that there is indeed some feedback here, right? Yeah, so I believe it should end up being negative, although I agree in the way I've drawn it, it's ended up being positive. But I think if we just include the output impedances, maybe that'll fix the problem. But nonetheless, indeed, there is a feedback loop here, right? Say that again? Oh, yeah, no, actually, no, I think I got the cap directions correct because, right, you do need to do negative feedback, right? And this would be a negative feedback on the capacitor. So I think I got that right. But nonetheless, maybe the more important point that I was trying to get at was that essentially, if you have this tail current source here, right, if it's really an ideal tail current source, then even if I yank these common modes around, it's not really going to do anything to the tail current source, right? It's not really going to change its value, right? So in other words, I can move the common mode at the input around kind of any which way I want, and that's not going to have any real effect on what the tail current source is doing, right? And so the problem, therefore, is that if you really have this always as a milliamp, and this always is 490 microamps, you can futz around with the input common mode all you want. You're still going to have this problem of the output being railed one way or the other. Okay? Even if you sort of ignore or you don't actually use this kind of ridiculous situation where everything's ideal current sources, the point is only to say that you typically build your differential amplifier so that it has high common mode rejection of its input, right? So that means that even if you happen to be getting some feedback back to the common mode of the input, if you are intentionally rejecting that common mode, then that feedback is unlikely to actually help you at all in terms of setting the output common mode. Okay? Does this make sense to everybody? Or yes?
I think I'm a little unclear on how maybe first I'm still a little unclear on how the feedback would help in the first place, because I still don't see that it's negative.
Yeah, no, so in this case, it probably does not, but I'm saying let's imagine somehow I engineered a situation where indeed the common mode feedback turned out to be negative. Okay? The only more important point I was really trying to make was that because I'm trying to use a tail current source in the first place, even if I could engineer a negative feedback signal to show up at the input of the OTA in the common mode, it still probably wouldn't help me very much, just because my whole point of doing this in the first place was to reject that input common mode. Meaning my loop gain in the common mode would be extremely small. And so therefore, even if it was negative, I basically couldn't really do much of anything anyways. Exactly. I still have the same current coming out of this tail current source as I would have had regardless of that input common mode variation. That's really the most important point. Yes? Okay, great. So you actually answered a question I was going to ask in about a couple of slides anyway. So, but since you brought it up, let's talk about it now. So what you were saying was that, well, hey, wait a minute. I've got this thing in like a capacitive feedback, right? So what that means is that if there was some bad initial condition on the gates over here, relative to what the outputs were doing, there's really no way for you to tell the difference between that initial, like you can't really reset or fix that initial condition, right? In other words, all these capacitive feedback is really doing is it's saying, well, if something changes at that output over there, it would then cause a change at the gate. But if I got into a bad initial state in the first place, the capacitive feedback wouldn't help you at all, right? That's basically what you were saying. Is that correct? Yeah. Okay, great. So yes, indeed, I completely agree. If you have capacitive feedback like this, that also would not change a DC biasing error. All right? So at the end of the day, what you really end up having to do is essentially, again, what we had said a long, long time ago was the way to solve almost all analog problems, which was add some feedback, okay? Or add some explicit feedback. So here what we're going to do is we're going to say that, well, look, if we've got this common mode that's undefined, let's actually add something that will explicitly sense what that common mode at the output actually is, and then adjust some knob within the circuit to actually fix that common mode to be where we want it to be. Okay? So what I'm going to do now is briefly walk through a couple of the sort of means by which you can do that sensing, and talk about some of the trade-offs there. I'll then mention basically what the knobs are to actually change that common mode, and then we'll look at a couple of practical examples as to how you would really actually do this in an actual circuit. Okay? So let's just start out with the sensing part of it. So it turns out that the simplest way to detect common mode is actually basically just to add a couple of resistors across the differential output. Okay? And the reason this works hopefully is fairly obvious, right? So if we look at, for example, what happens if I have a differential signal, where, as an example, this side goes up and this side goes down, right? Then as long as those resistors are matched with each other, this center point here basically is a virtual ground, right? Nothing really should be happening if I take the two sides of the resistor and I just move them up and down in a balanced way, right? On the other hand, of course, if I have a common mode variation, meaning both sides, for example, would go up, then now my common mode at the center also has to go up, right? Because there's no other path to ground, so two sides go up, it also has to move. Okay? Make sense to everybody? Or? Okay, so that's easy enough. The only sort of bad thing about this is that, well, actually there's a couple of bad things, but the first bad thing is that, of course, as we had said before, if we're really building OTAs, we tend not to like to put resistors at our output, right? Because those resistors just reduce the actual open loop gain we can achieve. Okay? So that's kind of bad news. Now, one way you could imagine to try and solve that is to say, well, okay, fine. So why don't I just make those resistors really, really big, right? So as an example, let's say that I'm going to make these like, I don't know, a teraohm or something like that. Okay? So what would be the problem with making those resistors be a teraohm? Okay, well, you might need a big chip, although, by the way, there are some clever things you can do to actually get a teraohm of resistance. They're typically sort of bad for various reasons, but, let's even ignore that. You are right, though. The chip might be big. What else is bad? Noise. Okay, you're right. There might actually be, indeed, a lot of noise from it. Let's even ignore that. Bandwidth, okay. So why is the bandwidth bad? Yeah, exactly. So the point is that, indeed, remember at the end of the day, if I'm doing some common mode feedback, sort of implicitly you're going to take that output over there and feed it to the input of some other amplifier, right? Well, when you feed it to that input, guess what? That amplifier always has some input capacitance associated with it. And so indeed, if you make those resistors absolutely ginormous, then the bandwidth of that feedback will be very, very slow, simply because you'll have to go through that RC filter, right? So now, here's maybe the question for you guys. Is it a problem that the bandwidth of that feedback is really, really slow, or not?
Depends on your common mode input bandwidth, I guess.
Okay, so you said it depends on your common mode input bandwidth. Or maybe more generally, it depends on the common mode disturbance bandwidth, right? Because if your common mode was completely stable in the first place, then yeah, who cares? Just make this really, really slow, right? But if your common mode actually could vary quite a bit, then you can't actually really tolerate this, right? Now, by the way, in our switch cap amplifiers, it turns out that oftentimes the common mode does actually have pretty big glitches in it, okay? If nothing else, because A, you have those switches in there, and as we'll talk more about later, anytime you turn those switches on and off, they tend to create glitches. But B, you should also keep in mind that no tail current source is actually ideal. There's always some parasitic capacitance and things like that there. And so whenever you sort of apply the inputs into the amplifier, particularly if they're not sort of perfectly differential, meaning they have a little bit of common mode excitation in them, there's going to be some time where the intrinsic common mode rejection of the amplifier is not really that great. Okay? And so in particular, if you have some glitch that shows up at that tail node there, you'd want to make sure you build your common mode feedback loop fast enough to basically deal with that glitch so that it doesn't end up showing up through some asymmetry or something like that as a differential error at your output. Okay? So in general, the take-home message is that oftentimes, especially for these, let's say, general purpose kinds of things, you're going to want to make the common mode feedback loop bandwidth fast enough to basically track with the main bandwidth of your differential circuit. Okay? Because if you do that, much like we discussed many times with the pole zero doublet, you can then make sure that there won't be any weird slow settling dynamics due to some other error that you just weren't thinking that carefully about. Okay? Make sense to everybody? Or? Okay, so we said that there was kind of this issue with this resistive thing, which was, again, that we would basically be loading our output. If we didn't want to load the output, we had to make the resistors big. That meant the bandwidth might be too slow. So, of course, there are other ways that people have come up with to do this common mode sensing. And one particularly sort of, let's say, interesting and in some contexts popular way of doing it is actually the circuit that I'm showing you here. So the idea is actually quite simple, and it's in many ways very similar to what we had done with the resistors themselves. So essentially what I'm doing is, you can think of this as kind of half of a source follower, and this is another half of a source follower. Okay? So the idea is what I'm trying to do is I'm just trying to take the output voltage on each side, buffer it through this source follower, and then if I just short the outputs of those two source followers together, it's kind of like I'm trying to take the average voltage between those 2 points. Right? So in other words, you can think of this almost as an equivalent small signal model of I have sort of input, let's just call this VO plus, VO minus. I'm sort of trying to take VO plus and VO minus, and then the source followers, of course, have some output resistance. But then if I just tie those two things together and look at the output, then indeed, as long as the 1 over GMs of those two devices are the same, the output should basically just be A plus B divided by 2. Right? Or VO plus VO minus divided by 2. Okay? So this is kind of just another way of really building that resistive sensor. It's just that now I'm doing it through this source follower as a buffer. Okay? So indeed, this actually works reasonably well. This now allows you to sort of not really load the amplifier, at least from a DC gain standpoint, right? Because I really am just using these source followers as buffers, and they, generally speaking, have reasonably high input impedance. But nonetheless, this is still somewhat limited in that if you really want this to work, you need those source followers really to behave essentially as good linear buffers, right? And unfortunately, there's only so much sort of input swing you can put into that source follower before it won't really behave as a good linear buffer anymore, right? So in particular, let's just think about what happens as one side of that amplifier gets very low. Okay, and specifically, let's ask the question as, how low can that output from the amplifier go before this source follower would basically, in some sense, let's say turn off or really exit its sort of reasonable bias condition? So what would that voltage be? Yeah, exactly. So, and let's use our terminology that we typically use here. So there's something like a V star you need from that tail current source down there, right? And then you need another VGS across that source follower, where that VGS, roughly speaking, would be something like a threshold plus a V star, right? So in other words, if that voltage there ever gets lower than VTH, plus 2 V star, right? Then basically that source follower is going to start crapping out, right? It's basically going to start turning off and not really behaving in a linear way, all right? So the point here is only to say that, especially in something like a modern technology where, let's say, your V star was a couple hundred millivolts and your threshold was, let's say, 300 or 400 millivolts, that would mean this node here could never go below 7 or maybe 800 millivolts or so, okay? And if I've only got a 1 volt supply to begin with, that's kind of crappy, right? That means I really have to have very, very small swing at that output in order to get this kind of design to work, okay? So again, this works reasonably well, but it places, unfortunately, a bad constraint on the swing of our OTA. And in general, we'd like to have as wide of a swing as we possibly can and not be limited by our common mode sensor, okay? So let's look at another alternative, which hopefully you guys could have already been sort of guessing at, which was, if you remember when we had talked about OTAs themselves and we talked about OTAs and feedback, we sort of went through a very similar discussion of resistors were bad because they loaded the gain. So we said, well, okay, screw it. Why don't we just use capacitors, right? Because at least at DC, capacitors don't take away from our gain. And hey, at high frequency, we're going to have some capacitors there anyways for noise standpoint, so why don't we actually use them for some useful purpose, okay? So here, this is, again, sort of the exact same argument. It's just saying, well, if I use these capacitors just like I use the resistors, I can once again detect the common mode, right, without really creating a DC loading effect. Now, having said that, this goes back to one of these sort of comments that was made earlier, which is we do have to be careful about this, because if we really are using capacitors for the sensing, we can only really detect changes in the common mode, right? Because remember, at DC, these impedances are infinite, right? So just as an example, somebody could be mean and say that, you know what, I'm just going to decide that I'm going to send some random particle from space and have it land right at that point right there. And by the way, again, in case you think I'm joking, that's a real, actual issue. Random particles from space can affect your integrated circuits, okay? That particle just happens to land there, and guess what? It makes it sit at 10 volts, okay, just to make some number up, all right? So of course, if your outputs over here were nominally at, let's say, 1 volt, but that random particle just, made the initial condition on the cap go off somewhere else, of course, your feedback loop will not work, right? Because it'll just see some big DC error and completely do the wrong thing, okay? So again, the point here is just like with a capacitive feedback in our normal, let's say, differential mode, if we want to use capacitive feedback for the common mode sensing as well, you're going to have to do some kind of resetting to just make sure that that initial offset or that initial unknown condition doesn't completely mess you up, okay? So basically everything that I'm saying here is very much exactly in analogy to what we did in the differential case, okay? So as you'll see in a couple more slides, much like we did with the differential case, what we're probably going to end up with is topologies where we basically use switches and capacitors to essentially every single cycle reinitialize that sensor to make sure that we know it's actually giving us the information we're interested in, okay? Make sense to everybody, or? Okay. So, we talked a bit about sort of the different sensors, and we kind of converged on the capacitive one as most likely being the most attractive one. So now let's think about what we can do to actually adjust the common mode. In other words, in a generic feedback context, we need sort of a sensor and we need an actuator, right? Okay, so if we think about what we can actually do in our simple example here to really control the common mode, turns out there's really only 2 knobs, right? Knob number 1 is adjust the load current, and knob number 2 is adjust the tail current, okay? And really, if you look at this picture, indeed, that's really the only 2 things we can do, right? And of course, it doesn't really make sense to do both at the same time. You really basically only do one, right? Because all you need is basically for those 2 currents to match each other in order to actually set what that common mode really is, okay? So, let's look at an example of how we might actually do that. And in this particular case, I'm going to choose knob number 1, or knob A, I think I called it, which was to adjust the load currents, okay? So the way I've done that is indeed quite straightforward. And by the way, I chose to use the resistive sensor here just to make my life sort of simpler. But, don't worry too much. You can do this with a capacitive thing, and the trade-offs are very much the same. Okay? So the way I'm doing this is I basically just, these two resistors are exactly my resistive sensor. That's how I grab the common mode at the output. And then what I'm going to do is just feed this into some amplifier and use that to essentially adjust the tail current. Okay? And so indeed, as long as I've sort of set everything up correctly here, as long as this amplifier has good, DC gain and etc., it should be the case that I'm really forcing this VCM here to match that VCM ref. Okay? Now, just to make sure that we've sort of gotten one thing right, and to make sure you guys are paying attention, usually when we do negative feedback loops, you're used to seeing the sort of feedback tied to the negative input of the op amp. Notice here I tied it to the positive input of the op amp. So let's just double check. Was I correct or not when I did that? And let's see if somebody else will get it. Yeah. Okay, indeed, it's driving a PMOS, right? So notice, and by the way, even if it was driving an NMOS, the same thing would be, or an NMOS in common source, the same thing would be true. Okay? So notice, let's say that indeed the common mode at the output went up, right? Well, in the configuration I tied it, that would mean the gate here would go up. And because indeed I'm driving a common source amplifier, that would mean that the output would go down. So indeed, I am in negative feedback. So I did get that actually correct. Okay? Now, having said that, with any negative feedback loop, I need to be worried about stability, right? So let me ask you guys, what are the sort of poles that might exist in this common mode negative feedback loop? Or rather, what nodes might those poles be associated with? Okay, that's right. There's always some capacitance right here, right? So I'm definitely going to have a pole, and let me do that closer to where VBP actually is. I'm definitely going to have a pole at that gate control node there. Where else? Go ahead.
I mean, input cap at the plus terminal input.
Yeah, exactly. There's always going to be some capacitance here. So there's going to be a pole right there. Any others? Yeah, exactly. There's also going to be a pole, and now I'm going to abuse notation slightly. There's also going to be a pole essentially at the common mode of your differential output, or your differential OTA stage, right? And this is where I've abused notation slightly because that's really physically two nodes. But if it is a common mode excitation, then I should be driving both of those two nodes with the same signal. Okay, so ideally speaking, that should really just be creating one pole. Okay? All right, so indeed I've got now those three poles. And as usual, if I want the thing to be stable, then I'm going to have to make one of those be the dominant pole. Right? In other words, at roughly the gain bandwidth of the loop, lower frequency than all of the other poles. Okay? All right, so in this context, where do you think you guys are going to want to place that dominant pole? Or rather, which out of 1, 2, and 3, which one do you think you're going to want to be the dominant pole? 2, okay. So why'd you vote for 2?
Because you want those resistors to be large.
Okay, so you said 2 because you want those resistors to be large. There's some truth to that. Let me just do something a little bit interesting. So let me say that I make those resistors really big. Well, actually, no, before I do that. So fine, let's make that true. Okay? So let's say we make those resistors big. What is that going to say about pole number 1? What are you going to have to do in pole number 1 to make sure that the thing is stable? Yeah, you're going to have to make sure that the GM of this amplifier relative to that capacitor, or really the output impedance of that amplifier relative to that capacitor, gives you a time constant that's much, much faster than whatever this time constant on this node is. Right? Why do I claim that that's actually potentially a little bit bad news? Or rather, why does that kind of annoying from the standpoint of building the lowest power design I can possibly build? Yeah, I basically have a constraint on how small I can make this GM. Right? And that constraint is then tied to sort of how big I can actually make this resistor, how much cap is actually placed here. And in fact, it kind of goes, right. Anyways, what it really is just saying is that if I place the dominant pole right there, then now that GM is really constrained to be sitting at somewhere that's way, way higher than where you want the dominant pole in the loop to actually be sitting. Right? So in other words, I probably have to spend more GM than I otherwise would have had to spend just to get this thing to be stable. Okay? So anybody else has a vote as to where they want to put the dominant pole? Oh, 3, really?
There's already a dominant pole there from the differential.
Ah, okay. So now this is another interesting one. So 3 indeed has a pole in it due to the sort of differential amplifier itself. That's absolutely correct. However, in this common mode feedback loop, what did we say we wanted the sort of overall gain bandwidth to be relative to the OTA? Is it low? Yeah, we want them to be about the same just to make sure that this whole thing settles out quickly enough, right? So, by the way, if I place it here, what does that again say about the sort of GM of this thing here? Yeah, it also has to be high, or rather high enough, to make sure that its pole, open loop, is far enough away from your closed loop gain bandwidth you wanted from the whole OTA, right? So in other words, if you place the dominant pole, and by the way, I guess we've gone through all of the options already, so it turns out number 1 is indeed the one I think you want to choose. If you place the dominant pole anywhere except at the output of the OTA, right, or rather of the amplifier, I should say, then what's going to happen is it's going to force you to spend more current in that amplifier just to make sure that it's non-dominant relative to everything else. Okay? Whereas if, for example, I really place the dominant pole right here, then I really just have to choose the GM of that amplifier just based on making the gain bandwidth of that whole feedback loop high compared to the gain, or rather comparable compared to the gain bandwidth of the differential part of the circuit. Okay? So in other words, by placing the pole here, or placing the dominant pole here, it's allowing me to spend just enough power to meet the constraint I cared about, and not any more than I otherwise would have had to. Right? Because again, if I make the pole somewhere else, those poles would have to been set at the same place as this pole would have been, right, to get the same gain bandwidth. And then I would actually have to increase the power I spend in that amplifier just to make sure that it does not become the dominant pole. In other words, that common mode loop remains stable. Yes?
If you want the dominant pole to be at 1 anyway, then why did you say a couple slides back that big resistors slow the common mode track?
Oh, well, because notice, if this is where your dominant pole is supposed to be, right, if I make these too big, now my non-dominant pole will screw me up, right? Because I'll have another pole due to this common mode tracking, or common mode sensing, I should say. Does that make sense? Or Rachel, you had another question? Okay, great. So, by the way, there's another trick that we can play, which is kind of going to be mixing between what we've said we were going to do in the first place. So, it does turn out that you tend to like to make these resistors big, okay? Because, again, you don't want them to load your amplifier, and we'll see a little bit later how we're going to do this with sort of switches and capacitors and things like that. But there's another trick that we can play that we actually talked about, again, a couple lectures back, as to actually exploiting zeros in an interesting way. So let's say I indeed wanted to make that resistor big, but I wanted to make sure that still at high frequency, my common mode signal actually makes it into the input of my amplifier. What could you add to this? I heard somebody say it. Yeah, capacitors. How are you going to add capacitors to solve that particular problem? Yeah, exactly. So imagine that I just put a cap in parallel like this, and another cap in parallel like this, right? Now, and as we'll talk about in more detail in 1 second, if you make those caps large enough compared to the cap that's sitting out over here, then even at high frequency, instead of going through the resistors, you just go through the cap to actually make it to that feedback node, right? So notice, by the way, that adding those caps in there was exactly just adding a 0 and trying to exploit the fact that by adding that 0 in, I could basically get extra bandwidth from this sensor circuit. And just as a reminder, this is exactly the same sort of trick that we had been talking about in the context of the oscilloscope, right, where we had that resistor divider and we just added a cap around one of the resistors, exactly to get higher effective bandwidth out of the circuit. Okay? Make sense to everybody? Or? All right, so now let's take a look at how we might actually use this in a somewhat, let's say, practical context. But actually, before I do that, there is one thing that I should mention here. Okay? So, and let's actually go back to even this part here. So we said that there was really 2 knobs we could adjust, right? And I showed you one of them. The knob I showed you was adjusting the load current. Okay? it turns out that oftentimes you're not necessarily going to want to adjust the load current like this. You're instead actually going to want to adjust the tail current source. Okay? But to understand why that is, we have to sort of keep in mind one thing, which is, remember, at the end of the day, the whole reason we care about the column mode was really only one of two things, right? One was we want to make sure that it just doesn't end up somewhere that's horribly bad and the whole amplifier doesn't work. But the second is to remember there's always going to be some asymmetry in your circuit, right? And if there's asymmetry in your circuit, then that means that anything that you apply to the common mode will get converted into the differential mode, right? That was that sort of ACDM that we had talked about, okay? So again, keeping in mind that your circuits are never going to be perfectly symmetric, why is it that you indeed might prefer to actually adjust this rather than adjust the load current up over here? Why are those two kind of different?
The one is 2 transistors, the other is 1.
Yeah, exactly, right? Up over here, I'm adjusting 2 separate transistors, right? And if they matched each other perfectly, then indeed, the current should just be a purely column mode current, right? But let's just say that as an example, and let's do it on this slide over here. Just as an example, let's say that from whatever reason, this width was W, and this width was W plus delta W, right? Well, now by adjusting that control voltage right there, you will indeed be creating a differential current of delta I at the output, right? Question or yeah?
I mean, doesn't that differential current sort of already exist regardless of where you device?
When you say that differential current already exists. So the point here that I'm getting at is that if these two mismatch, then when this common mode feedback loop acts to try and adjust a common mode, it won't be able to only adjust the common mode. It'll have to create a differential signal to do it. That's what I'm getting at, right?
There's still a differential signal existing just due to the mismatch. Like if the two were mismatched and you just had a constant bias, you're still getting something.
Oh, it's certainly true that if there is some mismatch in the sort of, let's say, resistance of those two structures, that would indeed also lead to a differential error. So if what you're saying is that by adjusting this, if these two ROs are different, then that would cause a differential error, that's correct. But notice that if I really had an error like this, what's probably even worse is that now I actually have GMs that are different. In other words, for some small adjustment in the voltage here, I'm actually going to get a GM of delta I. Whereas in the other case, it's more just the ROs are slightly different. So as an example, if the RO was dominated by the RO of the transistor itself, that might even be completely knocked out. Yes?
What Rachel was trying to say was that even if you don't do any common mode feedback, you're still going to have differences load current.
Right. No, so that's absolutely correct, that even if you didn't do any common mode feedback, if you just had sort of some slight asymmetry there would indeed be some, let's say, asymmetry in the structure itself, meaning that if you applied a common mode signal just at the input, it would cause a differential error at the output. The only question is that if you now have this asymmetry here as well, and you tried to correct the common mode, by trying to correct the common mode, you could actually create even more differential error. That's really the point. Okay, great. So, point here only being that oftentimes you'll want to essentially create a structure where when you adjust the common mode, you'll try and do it at the point where you really just have a single element, right? Just to try and eliminate some of those asymmetry effects. Okay? So that's why if you notice in this sort of next structure that I'm showing you here, I've actually moved to this so-called capacitive common mode feedback where rather than adjusting the load currents, I'm now instead just going to be adjusting essentially the bias of this tail current transistor over here. Okay? So what we'll start sort of talking about briefly now and we'll finish up with next time is it's useful to look at this kind of structure to start sort of figuring out what are really some of the underlying design trade-offs in doing these common mode feedback loops. Okay? And in particular, the interesting question that I'm going to maybe leave as a sort of homework question to you guys, and you'll get even a full spring, well, yeah, basically almost a full spring break to think about it, is how would you actually choose the size of these common mode feedback capacitors in order to get the sort of loop characteristics that you'd want? Okay? So in particular, as is already highlighted on the slide here, if you make these capacitors too small, then what will happen is you'll get essentially a capacitive divider between basically your input common mode and the feedback signal, right? In other words, you'd be attenuating the common mode variations at the output before they make it back to this sort of bias point of the transistor. And notice here, I didn't really explicitly put an amplifier into this system. I'm just using the tail current source itself as the quote-unquote amplifier. Okay? So again, the trade-off here is that if I make these capacitors too small, then I will basically be losing common mode feedback gain, right? Which would mean that somehow I'm going to have to make up for that gain somewhere else to basically set my overall settling accuracy. Okay? On the other hand, though, of course, if I make these capacitors too large, then what will happen is that they will just look like a differential capacitance as loading my output, right? And if they're really big compared to the capacitance I wanted in the first place, then I basically just have to drive those capacitors, even if I didn't necessarily have to do that for all of the rest of my differential circuit. Okay, or really, I should say, even if my differential circuit didn't require that large of a feedback capacitance. Okay? Does this sort of make sense to everybody, or? Okay, so I think actually Pierluigi will pick up with this on Thursday.